This is lecture 8D on probability density functions for Calculus 2. Now I'm going to talk about just a group of exponential density functions and calculate some of the results so you get used to seeing how this is done. Let's start with this decaying exponential, a e to the minus ax. This is the probability density function here that we're talking about, and the domain is all x greater than or equal to 0. Is this a probability density function? Well, it's positive everywhere, so it satisfies that requirement. And then the integral from 0 to infinity, which will be calculated later, of e to the minus ax dx is actually equal to 1. Okay? So it does satisfy the requirements to be called a probability density function. And we need to know the median and the mode. The median is 1 over a being this coefficient here. Okay, and the median is the natural log of 2 over a. Sometimes this is rewritten as 1 over mu e to the minus x over mu. In that case, you can just read off the median. Read off the mean. All right. I'm going to calculate now the mean and the median for this distribution function. The calculation of the mean. Okay, mu is the integral over the domain of f of x times f of x dx. This is the general definition for the mean. All right. In this case, f of x is a e to the minus x, so mu is the integral from 0 to infinity because the domain of f was all x greater than or equal to 0, so that's why I'm integrating over the entire domain. All right. And I take that probability density function and I multiply it by x. There's the x right there. So it's ax e to the minus ax dx. To carry out this integration, we need to use integration by parts. Here is the substitutions that I'll use. Let u, that dx doesn't belong there. U equals x and dv. Okay, so what I'm looking at is u dv, and I have to calculate 0 to infinity. This is going to be u times v evaluated at 0 to infinity minus the integral from 0 to infinity of v du. So I need to select u and dv. For u, I'll let u be x, and dv is a e to the minus ax dx. Differentiating the u, du equals dx. Okay, integrating dv, I get v equals minus e to the minus ax. Substitute that into this form, I will have that this integral here, integrated by parts, equals minus x e to the minus ax. That's u times v. Here's u, and here's v multiplied together, evaluated at infinity and 0, minus the integral of v du. V is minus e to the minus ax, du is dx. Now this first term here is 0. You can work that out. That's pretty easy. Now we're going to evaluate the integral. I've got the integral from 0 to infinity of e to the minus ax dx. That equals minus 1 over a e to the minus ax, evaluated between 0 and infinity. Negative signs, and all these negative signs are half a problem. At infinity, the exponential is 0. So the first term is 0. Minus the value at the lower limit of integration, which is x equal to 0. At the lower limit of integration, e to the minus ax is equal to 1, so this becomes 1 minus, parentheses, minus 1 over a, which equals 1 over a, and that's what we had before. This is our calculation for the mean. It was an instructive calculation because it required integration by parts. It also required looking a little bit at the limits of functions. Now let's calculate the median. Okay, here's the calculation of the median. So to calculate the median, I'm going to look from 0 to m of f of x dx. Okay, and we want to find m such that the value of this integral is 1/2. All right, substituting f of x here, our probability density function of a e to the minus ax. For f of x, we're going to integrate from 0 to m. This will be actually not always 0, but in this case it is 0. 0 to m, or I could have gone m to infinity of f of x dx has to be 1/2. Okay. So I'm going to write it from 0 to m. Then evaluate this integral, yields negative e to the minus ax, evaluated between the limits of integration, must equal 1/2. Substitution gives me the second line. Take care of the signs, combine 1 and the minus 1/2, and this is what I end up with. E to the minus am equals 1/2. To solve for m, I'm going to take the natural log of both sides. This is a good trick. Always think about this when you have exponentials. Taking the natural log of this side gives me minus am times the natural log of e, which of course is 1. Here I've got the natural log of 1/2, which I can break out as the natural log of 1, which is 0, minus the natural log of 2. Dividing by minus a gives me that the median is the natural log of 2 over a. And that was the result that was quoted underneath this probability density function of the decaying exponential a couple slides ago. So we verified those results. At the end of this lecture, we'll use this distribution function to calculate failures of savings and loans. This is a more common, this is the Gaussian density function giving you the bell-shaped curve. Here f of x is 1 over sigma, sigma being the standard deviation, the square root of 2 pi e to the minus x minus mu, mu is the mean, squared over 2 sigma squared. Mu is both the median and the mean. That means the expected value here is mu. This is a wrong writing instrument. Mu is here. That's both the expected value, or mean value. It's also the median. Since the integral here is a half, here is a half. Okay. This is a very common function. However, it has no closed form solution. That e to the, what you're dealing with is this integral of e to the minus x squared, and there is no closed form solution. But it is so, it occurs so commonly, and it is so famous that the values are given as numerical solutions that are listed in tables of what are called the error function. So its integral is called the error function, and the values have been tabulated for quite a few years. Here's another uniform density function. If it has a magnitude of, it's a square distribution function. It's uniform, meaning that all values between a and b are equally likely. Here f of x is 1 minus b over a. It's necessary that the height of this function is 1 minus b over a, so that the integral from a to b of f of x dx equals 1. Notice it's already positive, so it satisfies the first property of a probability density function, and now the integral over its domain has to equal 1, and this is the second criteria. All right. The mean and the mode are both b plus a over 2, and that's pretty obvious. That's just halfway. Okay, there's b plus a over 2, midpoint here. The area under this curve is divided into halves at that point. Also, that is the expected value. To find it, you could integrate from a to b of x times f of x dx. This is going to be that mean. All right, keep going here. F of x is 1 over b minus a. I can write that out in front. And I'm integrating from a to b of x dx. This gives me x squared over 2 times b minus a evaluated between a and b. So we have here b squared minus a squared over 2 times b minus a. You can factor b squared minus a squared. I'm going to continue the calculation up here. So I will have b minus a times b plus a divided by 2 times b minus a. These cancel, and we get the result that's stated here. There's another group of probability density functions called the beta density functions. Here's some examples. In general, this function for beta greater than 0 is quantity beta plus 1 times beta plus 2, x raised to the beta times x minus 1. And here's an example of what these functions look for different values of beta. This is for beta equals 0. You have this, looks triangular, beta 0.5. This one is beta equal to 1, and beta equal to 4.